So a brief introduction and profile of David Smith. After graduating with a master's degree in computer and electronic systems from the University of Strathclyde, David Smith has worked in developing and delivering distributed energy resource management solutions with smart grid solutions. He is now responsible for the technical delivery of projects and has the experience in delivering innovation and business as usual solutions for utilities, public sector organizations, research institutions, and the private sector in the United Kingdom and North America. Please join me in welcoming David Smith for his presentation. Thank you.
Thank you for having me along. Let me just see if I can share my screen, and I will go through the presentation that I have prepared. Look here. Let's see if you can see it now. Can everyone see my screen here? I believe so.
Not yet.
Not yet.
Yeah, not yet.
Oh, I see, actually. There we
Yeah,
go.
there you go.
That's maybe better.
Yeah, there you go. That's it. That's your screen showing up now.
Yes, super. And you can see the presentation screen, I presume.
That's fine. Yes, we can see it.
Fantastic. Fantastic. So yes, I won't repeat any of the things that have been said about me, but yes, so I work for a company called Smarter Grid Solutions. We work in the energy sector in the UK. And let me just go on to the next slide, actually. So we're based in Glasgow. We work in the energy sector, delivering something called distributed energy resource management systems. We'll talk a little bit exactly about what that means. But Smart Grid Solutions started about 11 years ago, span out from Strathclyde. We develop essentially software to manage energy resources that are connected to the distribution network. We're based in the UK, US subsidiary offices, and we also have recently been bought over by Mitsubishi Power Products. And yeah, mostly software based. My role in the company is I'm in charge of taking the software and making sure it's delivered to our various customers, as you can see in the map there, and make sure it meets their needs and is delivered in a technically sound fashion. Give you a quick overview of what we're going to talk about today. So I'm aware this is a multidisciplinary group. So I'll give you a quick overview of the power system as it relates to the conversation we're going to have today. And I'm going to talk a little bit about the different areas that I am interested in, the different areas that we develop software to help with. So we'll talk a little bit about the problems that we see in the distribution network and the different ways we solve those problems. So overview of the problem, overview of management system, and then looking at some case studies, and finally looking at the challenges in the future. And we'll get a space for some time for questions at the end, so I'll be very happy to answer those. So, as I said, a very high level overview of the power system. I'm sure this will be familiar to many of you, but just important to make sure everyone knows what I'm talking about. I apologise if I mention a lot of acronyms, as with most technical industries. You have your own set of acronyms. I'll try my best to define them as I go through. So essentially a power system is, as the tagline there says, it's the means by which electrical energy is transferred from a generator to a demand. And the image you see here is a very high level overview of the standard arrangement, traditional arrangement of power generation across the world. And part of the problems I'm going to be talking about today are when we are diverging from this standard model, and the different things, the different problems that crop up there, and different ways we can solve them intelligently. So in the far left, traditionally, they start off with centralized generation, goes through some big overhead lines called the transmission network, down to the distribution network, which supplies the local demands. We'll look at each one of these. So generation, so as the name suggests, it's the methods used to make energy. Typically, the majority of energy, electricity production, is in large-scale centralized generation sites. So most countries in the world, things like rooftop solar isn't the primary source of energy. It's centralized large sites like large gas turbines or large nuclear plants, and those tend to be located close to the areas where the energy is needed or where there's abundance of resource. So out in the desert where it's sunny, out in the oceans where it's a bit windier, you can get big offshore wind farms. And this is, again, to stress, this is the traditional way that networks are designed. And essentially, energy is taken and is shared between all the large generation sites and transmitted across the country using large highways is how we describe it here, large transmission networks. So we recognize the tall transmission towers. And for example, in the US, there's 3 transmission interconnections. There's kind of 3 separate networks that are interconnected. And in the US, each state manages its own portion of the transmission network. So the transmission network isn't quite my area of expertise. Where we are interested in from Smart Grid Solutions and where I've got my knowledge is in the distribution network, and that's essentially the kind of step down from the transmission network. So the voltages are lower, the cables are smaller, but they tend to be more complex and therefore sometimes more difficult to plan and to actively control, because they are larger in scope and more wires, essentially, and more branches. And essentially, the idea from the distribution network is it takes the power that's been centrally generated and then passed around by the transmission network, and there will be different distribution networks in the places where there are people or there are places where power needs to go. And so the idea is the voltage is lower there, closer to what you would use in your house, and at the level that you'd use in your house, and they are more complex because there are, especially in cities, can become very complex. And so the challenge for active control and the challenge to do smart things there can be a little bit more difficult. Finally, demand. When I say demand, it's essentially anything that's using needs the electricity. So we would refer to all consumers of electricity as demand, because they demand power from the grid, or they also refer to them as loads. In the US, pole top transformers would bring the power lines electricity down to 120 volts for the house. In the UK, things are a little bit different, obviously different voltage level, and we don't tend to use pole top transformers as much. And things like rooftop solar, so any domestic electricity connects at this level, and yeah, power's measured by meters installed at each location, each connection point. And to provide us a little bit of context here, so the electricity, the way it's used today, is essentially a product of history. So this is a little bit of an overview of where we've got to today and why we've got there. So the different steps we've been through In the very early days of electricity, it was all very decentralized, local, small networks, with small generators distributed around about the users of the electricity. For various technical reasons, the voltage levels would rise over time to make it easier to transfer the power, and you would get bigger generators locally, and then essentially those little networks would join together, and then they would that would continue over time for various reasons. Some of the ones listed in that bullet point 3, security, and we say security there, we're talking about security of supply, so you're less likely to get to lose your connection if there's more paths for it to follow, and you get various economic reasons for that as well. Generation tends to scale up. Historically, the most efficient generators tend to be quite large. It's difficult to build, or difficult with our current technology, to build a small nuclear plant. Hydro tends to be quite large as well, so you see a great drive to centralization. And that's what drives the current network planning as it is. When I was talking about centralized generation, transmission networks and distribution networks, and various other things, deregulation, then there was a great swap over in the last 20 years from coal moving towards gas. And then more recently, there's been a big pickup in renewables, which has driven a change back to decentralization. A lot of the renewables we're seeing, they're smaller scale, they're connecting onto distribution network, and that's essentially what we're going to be talking about today. So my favorite acronym, potentially, DER, Distributed Energy Resources, and essentially that is what I'm going to be talking about mostly today, the management of these distributed energy resources. So it's essentially an energy device that is located on the distribution network. So if you remember when I was previously talking about the traditional way, big centralized generators, connected transmission network, and that's how networks have been planned for a great number of years. And that means with the advent of distributed energy resources, some of the original planning assumptions are no longer true. And we'll talk about what that looks like shortly. So distributed energy resources, as I said, things connect to the distribution network. So there's great opportunities there. There's lower losses because they're closer, they can be closer to the demand. You're generating power local to where it needs. You can use DER to support and improve the networks through some smart technologies. And DER tend to be driven a lot by green technologies, so small scale wind farms, say, or relatively small solar farms, things like that. But there's a lot more. There's a larger variety of challenges as well. So as I said, the network is planned with specific assumptions in mind. The main assumption I'm going to be talking about today is that they are planned with the assumption that power is coming down from the transmission network down to the distribution network. When you add a lot of generation onto the distribution network, that assumption is broken, and you need to have greater control and greater understanding of what's happening. So backfeed is what that refers to, technical term. Referring to that, you have to be careful with more generation and distribution network to make sure things don't get damaged. And also, when you're talking about a lot of small scale, relatively small scale generation, the network operators traditionally, they find it very easy to control the large centralized generators, because they would just phone up to the control room of the centralized generator and say, turn down please, turn up please, or do whatever they need to do. But when that is replaced with maybe 100 small wind farms, or maybe a large collection of rooftop PV, that becomes much more difficult to do. And so essentially what we do at SGS is we develop software to help manage these distributed energy resources. So these energy resources connected to distribution network. The company started span off from Strathclyde, as I mentioned, to in response to a PhD project that looked to help wind farms connect in the Orkney Island. We'll talk about that in one of our case studies. But yeah, the main tagline there, it's got lots of wind, but not many people. So the big problem there is getting the power off the island to where the people are on the mainland. And we'll talk about that later. But essentially that is what we do, software to manage those resources. We have three main products. One which we sell to utility companies to help them manage from the kind of safety perspective of their network. Another product, so the first one's called Strathclyde. Another product called Cirrus Flex, which is we sell to DER operators to help them manage their large variety of assets and make the best use of them. And a final product called Strata Resilience, which is where we use our control system to very specifically help manage microgrids, which are small networks which can stand by themselves without being connected to the wider network. Slide on microgrids here. It's maybe a concept that's not as well known. So essentially it's a small section of a distribution network which can disconnect from the greater section, the rest of the network, and be self-sufficient. Traditionally that would be through maybe say a diesel generator, but more recently we're seeing greater access to say battery technology, renewable technology. So there's a much greater push to try and see how we can make that work, long-standing microgrids with renewable energy and batteries. Why would you want to do it? Well, if there's a blackout, if you've got some problem with the wider network, but your little section of network is okay, a microgrid would let you continue on. You see them most regularly in things like military bases, or somewhere where there's critical infrastructure. So in the US right now, there's a big push for the development of microgrids in areas where there are, say, wildfires, and there's a big push to kind of build microgrids around the emergency services there to allow them to fight the fires more efficiently and also have somewhere safe for people to go. And of course, it can be better if you're got lots of renewable generation, lots of cheap energy that you're not needing to import that from the wider network. Common microgrid locations, I'd mentioned military bases, but also universities, large companies or large factories can operate as their own microgrid quite regularly. We'll talk about one example of that, one case study of that later. I talk about DER, the common list of DER here. So PV, solar photovoltaic cells, can be as simple as a solar panel on top of your roof, or maybe a farm-sized piece of land. In the UK, solar is not as common as in, say, the US, where we've got a lot more solar under control. Wind, much more common in the UK. Because of the size of wind farms, they tend to connect to the distribution network. So a lot of the energy a lot of the customers we control are wind generators, and there can be other renewable types that are maybe a little bit less common. Tidal turbines, we've controlled one of them up north in Scotland. They're less common in general. Solar thermal and geothermal tend to be too large to really justify connecting the distribution network. They're closer to your more centralized. Much more common these days, we're seeing a big push for batteries, which are one of the energy storage technologies we see. Batteries and pumped hydro are probably the most common, flywheels not so much. Batteries are used to provide a wide range of services these days. We'll talk about that a little bit later as well. And another common one, electric vehicles. So they are distributed energy resources because essentially they act as a load when you are charging them, but they also can act as a generation source. And we're seeing more, we're seeing a greater push for vehicle to grid technologies that allows either the power company or the owner to use them in intelligent ways. Also buildings. So we're seeing more commonly that large buildings will have some sort of building management system. And if you have some control over the loads in your building, you can use that to make things happen on the network. Fuel power generators as well. They're somewhat less common, but again, the big ones are very big. But you do get small ones, say, to support microgrids or to support loads on the network. So that's what a DER is and where they fit into the wider picture. Essentially, this is a very busy slide that is essentially saying that it can be difficult to connect DER. And again, we're going to go through an example of why it's difficult to connect DER, but essentially when in the UK, in the US, and in most countries, when something wants to connect to the network, there can be a cost associated with it. Either to build new infrastructure or to strengthen existing infrastructure. So essentially, there will be, at some point, there will be a capacity. Well, there is a capacity for energy generators to join a network, and at some point that capacity will be eroded away by all the DER connecting, and someone's going to have to pay money to reinforce the network. And that becomes very difficult to do for small scale generators like DER. And so a lot of the problems we're seeing is how to get customers' DERs connected to the network. I'm not going to dwell on this slide. It goes in a little bit too much detail. What you're seeing there, those are publicly available heat maps in the UK of different network operators who essentially, the red areas, the darker areas, show where there's no capacity to connect DER on the network. The green areas, there's some capacity, and that's essentially, the green areas, there's some capacity to connect energy without spending a large amount of money to reinforce the network. And so there's a large pipeline for renewable generators. However, there's a small number of places for them to connect without spending an awful lot of money. And that essentially comes down to the traditional way that networks are planned. As I mentioned, they're planned with this assumption that you've got large-scale centralized generation going over this transmission network and down to the distribution network. In this example here, it's more of an American example. The terminology is more American, but this is an example of the problems we solve and the problem that makes it difficult for DER to connect to distribution network. So this is an example. So you see the diagram, centralized power station on the left. The traditional way the energy flows is through the transformer, the distribution transformer, down towards the loads at the bottom. So you've got an example of two houses and a commercial facility. So domestic, commercial. But the general idea is power goes all the way down. So when there's a larger amount of load, there's more generation on the, when there's a large amount of load, there's more power flowing through that transformer. The grid has to be balanced. The generation must equal the demand, and traditionally that all happens through centralized control of those big generators. And essentially, when the demand increases, the overall generation increases. When the demand decreases, the generation decreases. Fairly simple. There. This just gives an example. So a larger number of arrows showing a larger amount through. And now the important thing to note here is these networks are planned with the worst case scenarios in mind. So the traditional way of planning networks is that that transformer in the middle has to be able to support all the load on the network below it. And that gets a little bit more complicated when we add some generation down. We'll skip through this one. So we get this scenario now where we've also got loads down, we've got demand on the distribution network. Now we've also got some generation on the distribution network, and that means the equation changes a little bit. So there's now additional generation on the distribution network, and so there's less of a requirement for the power provided by the big centralized generator. How does the system balance? Well, the system still has to, you have to control something, and it still tends to be the big centralized generators that are providing the control. And there will be sometimes situations where there's very low demand from the houses or the commercial buildings, and then so we get the situation where the base assumption is flipped and no longer holds. So you get situations where there's a lot of generation, very sunny day, but the houses aren't using much energy. So then you start to see energy flow from the distribution network back up towards the transmission network. And this is the difficulty, because the networks were never really planned for that. And in order to plan for that bidirectional flow, it could be quite expensive, because you're having to buy more expensive transformers, say. And the difficult thing is this doesn't happen very often, but the traditional way of planning these networks is that you plan for the worst case scenario. So you plan for that low load scenario, but high generation scenario. And so traditionally, there will be maybe once in a year, maybe one day a year where this will happen. But that would mean if all three of these generators want to connect, they need to pay to reinforce that transformer to support that one day a year. And that can be very expensive. And that means it's difficult for some of these generators to connect. So that is not ideal. And essentially what we do is provide software to let us dynamically control that distributed PV, so that when the constraint does happen, that one day a year, instead of paying however many million to reinforce the transformer, all we do is we turn down the PV. It sounds very simple, but it can be difficult in practice. And we'll talk through what that means. So essentially, the traditional way of connecting generation is through you'd call it a fixed connection. So every generator that connects would have an agreement that they are allowed to generate whatever their agreement says. Maybe it'd be a 30 megawatt PV site. They would be allowed to supply that 30 megawatts whenever they want. Now, because of the reason we mentioned previously, that can make it very difficult to get connections. So in the UK, in the US, other places around the world, we're seeing this development of a concept of a flexible connection. So as I said, there may be one day a year where that worst case scenario happens. So instead of saying you have to pay to reinforce for that one day a year, we just say, well, your connection is flexible. So sometimes you won't be able to export as much as you like. And so it's basically making more realistic assumptions of what the generation is going to do. So the demand, the amount of energy used throughout the day changes, the amount of energy exported by the generator changes. And so those base assumptions, those traditional assumptions, don't really make sense as much. And so what you need to do, you need to monitor the network in real time. That's previously been quite difficult to do because of the size of distribution networks. It can be quite expensive to put a lot of monitoring out. You've got to manage the DER in real time. So you've got to make sure your DER are smart enough to be able to be controlled. And you need some centralized system to be able to work out when those generators need to be curtailed, when those generators need command sent to them. That goes into a little bit too much detail for us right now. But we've got this concept of active network management, which is the technology used to manage these flexible connections. And so the terminology you'll see through here are firm generation. So generation is always going to be connected to the network, can do whatever they like, or non-firm or flexible generation, which is distributed generation, which can be turned down when necessary. There's a number of benefits to a number of different people. So at the top there, it benefits the DR operators, the people who use the energy, because they've got a lower cost of getting on the network. It's cheaper for them. They don't have to pay to reinforce the network. It's better for traders, retailers, aggregators, because, well, there's more energy in the network now. They've got more renewables, which tends to be cheaper, and they can provide services to different people. It benefits the overall system operator, so the person who manages those big centralized generators, because they don't need to buy as much centralized generation. They have potentially more control over the energy usage down on the distribution network. In the UK, the distribution network operators, the people who operate those distribution networks, have an obligation to connect as many DER as possible, and also means they don't have to pay as much to reinforce the network. And yeah, I've already mentioned the DR operators. There tends to be 3 mechanisms in the UK historically for managing this type of flexible connection. So timed connections, where you have just some predefined times where they have to turn down. So you may work out that in the summer, that wind farm can't generate at the same level. So in the summer, it would have a reduced set point. And again, that's making quite a wide sweeping assumption.
David,
yes,
we'll have like 15 minutes to go. So
that's fine.
So that we can,
we'll go through
the question and answers as well. Well, go ahead.
That's fine. So 15 minutes and then question and answer?
Yes.
Super. That's fine. We'll go through 1 or 2 of the case studies then.
Thanks.
So 3 mechanisms normally: time connection, turn down at a predefined time in the year. Now, again, that's making some wide sweeping assumptions of what's happening. Intertrip, which basically takes real-time measurements, uses infrastructure that's previously would already exist, protection infrastructure that already exists, and basically makes discrete control. So your wind farm would either be completely turned on or completely turned off, depending on the measurements. Or you can do more complex active network management, which is what I have most experience with, where you're taking granular real-time control of the generation that's on your network. You're taking measurements real-time of where the constraints are. You're understanding exactly when those constraints are active, when they're going to be a problem, and you're only curtailing the generation as much as you need at the times where it's actually needed. So you go from lowest complexity in the left, but most wasted generation, to higher complexity in the right, but much less wasted generation. So just to look at that as go back to our example. So you've got this situation where your generation is quite high, your load is very low, and your energy flowing backwards up through the transformer is just too high. So the first traditional approach is to replace the transformer with a bigger transformer. That's very expensive, and that would have to be paid by the solar developers, and it would make their business proposition infeasible, make it unprofitable. So the other solution is you take some active control, and this is a real example actually. I've anonymized it, but this is a real example where we deployed our software A&M Strata, and essentially monitors the current flowing through that substation, through that transformer in real time. When the current gets too high, we essentially just curtail some of that generation down, following a specific order, and that means we're only curtailing the generation when they actually need to be curtailed. What I would say, there is a limit to how much you can unlock using flexible connections. So what you see on the left is the amount of generation that is available through static fixed connections. You can unlock an awful lot more using active network management, but there will be a point of time where if you have there's only so much you can connect under active network management before you're always going to be curtailing someone, and it's going to be infeasible for them economically to connect. So essentially what we're just trying to say here is there is a limit to how much you can connect without reinforcement anyway, but you want to use active network management to more efficiently use the resources you've got in the network. This is just a list of things that are useful for a management system. We won't worry about that too much. And we'll skip through this and we'll have a little look at some of the case studies that we have got here. So this is the original problem statement that we as a company did solve. So Orkney is a small island in the north of Scotland, or not really a small island, it's a collection of islands in the north of Scotland. It has a lot of capacity for wind, so it's very windy up there, but there's not a lot of capacity to get that energy back to the mainland where it can be used. So it's connected to the mainland using two subsea cables. The demand in the system ranges from 8 to 32 megawatts, isn't very much. So that means there's essentially a firm capacity of 28 MVA. So essentially with the amount of generation it was connecting, using the traditional planning methods, they worked out that if you wanted to connect anything beyond that 28 MVA, then you were going to spend £30 million to get a new subsea cable from Orkney to the mainland. And so there was a lot of interest from the farmers on the different islands here to build small-scale wind turbines, to build a wind turbine or maybe two on their land. And essentially what that meant is, under traditional planning rules, whoever was the one to connect that would cause the limit to be breached, that would trigger the need for that reinforcement, that one person was responsible for that £30 million bill, which basically meant that all the farmers that wanted to connect were not able to do so, which meant overall there was a lot more capacity there that was being blocked by that uneconomic reasoning. So the solution essentially was to actively manage that generation that wanted to connect. So the network was split into a number of different zones. All those little islands there, all the names are the names of the islands. The mainland there, they've got a funny thing where they call the mainland, the biggest island, they call it the mainland. So that's not Scotland. That's not the mainland Scotland. That's the mainland of Orkney. That's a little confusing thing that I find is important to explain. But so split into different zones, and those different zones have generation connected to each. Each of the little boxes there are points that were identified as being constraints on the network. And so each one of those points, 1 to 7, were identified as constraints that you needed to be managed in order to ensure the overall energy wasn't going to be too high. So this was deployed 2009. We deployed a distributed real-time control system where essentially multiple generators were controlled in response to measurements from those network locations that had been identified as constraints. So the big headline number there is that the system that was put in, the control system and all the associated telemetry and devices, it cost 500,000, while the reinforcement that it meant wasn't. So the reinforcement, which wasn't necessary, would have cost 30 million or just over 30 million. So you're still pretty much looking at a 30 million pound saving. So that resulted in 24 wind generators being able to connect with an aggregated capacity of 39 megawatt, which is a lot. And the other important thing to note about Orkney is it's got some of the highest capacity factor. So capacity factor is how much of the connection is actually used. It's so windy up there, you get an incredibly large capacity factor for these wind turbines that are connected. So they're generating close to that 39 megawatt more often than other locations in the UK. So that was a big win, and you can see how that might scale to other parts of the UK. And so this just looks at some of the technical things, the technical terms that were used. Essentially, each constraint, each measurement point was monitored, and essentially the logic seems very simple. There's more complexity behind the scenes, but essentially the measured value was compared against thresholds, and once the threshold is breached, you perform some action in order to bring the measured value down to a safe level. And you've got some margins between each of those thresholds to allow some time to perform the actions. This is a relatively complex graph, but it provides an example of what is happening on the network. I think this goes through, it does. So at that point there is a threshold breach identified. So the lines are not particularly useful, but at this point, so this is the measured value for the constraint. This is the threshold where we take action. And essentially at that point there, where the arrow points to, the threshold has been breached. So it means there's too much power going through the subsea cable to the UK, to the mainland of Scotland. And so our system automatically does some, performs some control actions in order to reduce the current down. So you can see the export from some of the generators is curtailed. That's curtailed all the way down. This one's curtailed a little bit. This one's curtailed a little bit as well. And you see in response, you see the power at the constraint dropping down. I think it's the current at the constraint dropping down to a safe level. And essentially, when things have settled, we let some generation on until things calm down a bit on the network. Another very similar case study. These are all actually innovation projects, so there's a lot of information available for these online. I won't dwell on this too much, but there's 2 A&M systems we put in the east coast of Scotland, Dunbar and Berwick. Dunbar, we were able to connect 48 megawatts of generation, which wouldn't have been able to connect traditionally. Berwick, almost 30 megawatts that we wouldn't be able to connect traditionally. Bit of an overview of the network. We won't dwell on that too much. There's some different examples in a bit. A very similar project down in England this time. We were trying some different, more complex scenarios. So key points here, it would allowed us to connect generators faster, 29-week decrease in connection time. The aggregate savings for the entire project were about 44 million compared to the traditional approach, and we're able to connect 55 megawatts. Won't talk about this too much, but it's the same problem as in the Orkney, just in a different location. We'll skip through these. We'll look at some of the different scenarios here. So a slightly different project where instead of solving problems for network operators, we were solving problems for DER owners. So this was a project called Adept, and it was based in the Thames Valley of England. And essentially it was a few different councils wanted to work together to work out how they could use all of their DER, mostly renewable assets, how they could work together and understand what their energy generation was from a centralized place and how they could more efficiently use it. So we deployed a cloud system for them that essentially gathered measurements, gathered data from all of their sites for a large number of sites, and really understood what they were using, provided a method for them to centrally visualize that. You can see the array in the right there of what distributed energy resources were monitored. The idea is that project will be extended to provide some control, some pictures of what that looks like here as well. and a picture of what that visualization looks like as well. The final case study we look at here, where again, different product we deployed, but again, all about distributed energy resources. So we've recently deployed a microgrid system for the Lac Mégantic project in Canada. So this is in Quebec, Canada. Lac Mégantic was a town which had a terrible rail disaster which damaged a lot of the downtown infrastructure. And as part of the rebuilding effort, they decided to build a microgrid in order to more efficiently use the resources they have and essentially use it as an experiment to understand how microgrids could help rural Canadian towns have more resilience. So they quite frequently have blackouts in winter. In winter, they have to regularly have polluting diesel generators. They want to understand how they can use renewable generators to run microgrids. And we essentially, you can see the different devices which were added on the network, but they were built the microgrid is built for two purposes: to operate as an island. So either going into a planned island, we know something's going to happen, or to operate as an unplanned island in response to some loss of connection to the wider grid. When you're operating as an island, our system does a lot of optimization to maximize the uptime when necessary. What you're doing there is you're understanding when to use the batteries, and you're also understanding when the buildings need to have their load reduced. But also, you have some benefits of running the microgrid and operating the microgrid when it is connected to the wider network. So you're providing services. So the GDP event at the bottom is providing services to the wider transmission network in order to reduce energy consumption when there are system-wide peaks, but also you're using the energy resources you have on the town level to reduce the local peaks in order to save money for the people who live there. Now, I think we're just about at time, so this might be a good time to ask questions. Essentially, before we do that, I'll just have a quick view for the future of DR in the UK. So essentially, there are a small number of areas in the UK which have these active network management systems, but essentially all of the network operators have now an obligation to roll them out to all of their locations. So we're seeing a lot more interest in these connections, and most DNOs have a large pipeline. It's becoming cheaper to build these energy resources, the distributed energy resources, and so there's much more interest for them, and also they help massively in the drive to net zero for the UK. We're also seeing different things happening where network operators are beginning to act more like system operators. In fact, they've got an obligation to act more like system operators, where they use the energy resources on their distribution networks to offer services. So you're seeing a lot more drive for these things called flexibility service markets from each of the network operators. That's a different and more detailed topic for perhaps another time. So yeah, does anyone have any questions?
Yes, thank you very much, David, for that wonderful presentation. It was very fantastic. You really diluted and gave us the real facts on the influence of smart grid on distributed network applying your software. So yes, everyone, thank you. Welcome to this session. I'll anchor the session for questions and answers. So we'll go this way. If you have your question, just raise your hand, and when I call you, you can unmute and ask your question. Then we also have some questions in the chat room, so I will start with those questions, David. The first question is coming from Bennett Oyinna, and the question goes, what associated hardware components are needed to deploy the ANN software? And it's asking, is it a web-based solution hosted on the cloud or an offline application?
Good questions.
Yes, I
Oh,
will.
there's more.
Maybe yes. Let's take so that because of time, we'll take like 3 at a go. So these are 2 questions, and then the third one is said in terms of capacity management with ANN. This is from Engineer Abara. When generation is more than load, how is agreement reached with generation companies on who turns off their generator, and how is the lost revenue due to the loss managed? Basically, his question is, when there is so much load that needs to connect to the network, so how do they manage the financial implications of giving the priority to which generation company? So those are the 3 questions.
So
I will say you can take these 3. Why?
Okay, that sounds good.
Yeah,
so to answer the first one, what hardware is necessary? So I mentioned earlier, one of the things that makes these systems more feasible is that it's now cheaper to deploy measurement devices onto the network. So the distribution networks can be quite complicated, and if you want to actively control the network, you need to have good visibility. You need to know what's happening at different points in the network. So one of the key things you need to have is measurement telemetry. That's usually deployed by the network operator, and there's been a constant push over the last maybe 15 years for network operators to increase their visibility of their network. So you need to be able to know what's happening in the network. So have devices that will measure currents, voltages at different points in the network, understand the topology of the network, understand which bits of the network are connected and which bits are not connected. Again, traditionally, that's less common in distribution networks because they're bigger, more complicated, it's more expensive. But for the actual control software itself, there's a number of different architectures that are deployed. Sometimes there are localized, sometimes we deploy localized solutions that are close to the constraints. So we would put maybe like a PC, an industrialized computer in a substation. Or maybe we would put, depending on what the customer requirements actually are, the area that's been covered, you might put a set of servers in a much more centralized location in order to control a wider range of sites. So most of our software runs on servers. We do also deploy some much smaller devices for much smaller problems that would be based on an RTU or PLC. So that explains the hardware that's required. The next question I think was where they're hosted or whether they're cloud-based. So it's kind of a similar answer to the first one in that the software can really be deployed anywhere. Because of for the active network management, when you're controlling and resolving constraints, they tend not to be cloud-based because you want reliable hardware close to the problem. The real fragile bits of these systems are the communication links between different parts of the system. And distribution networks can go over quite wide areas. So you need to have good, robust communications. So we tend not to deploy cloud systems for constraint management problems, but we would have servers, say, in, as I mentioned, a substation or maybe some centralized, somewhat centralized location there. And they would use typically industrial protocols such as industrial internet IP-based protocols to solve these problems. You are seeing more of a push these days to control smaller generators using more familiar web-based protocols. So you see much more of a push for the acronyms Internet of Things, IoT. So IoT protocols to manage things, to manage devices, say in your house or smaller generation. And the final question, yes?
Yes, the third question was how do they manage to prioritize the generation company? So who kicks in and who kicks out? And how do they manage the commercial?
So the balance, so there's a few different levels to that. The balance of load versus generation is still overall managed by the system operator. So the system operator still is the person who is responsible. So in the UK, we have the system operator is National Grid, ESO. They are the energy system operator who are responsible for making sure the amount of generation on the network balances with the amount of load. And essentially what they do is they have a market which has been built up. So they have services. And so people basically say, you can turn me down if you want, but you have to pay me. And there is a full system. So there's a balancing market is what it's called. There's a full system for managing that that is managed by the ESO. Down on the distribution network, when we're talking about active network management, we're not so worried about balancing load and generation. We're only worried about making sure the constraints are not breached. And essentially, the decision for who is controlled at that point, there's different ways to do it, but in the UK, there are firm regulatory, there are firm rules that say basically the person who connects first is the last person to be curtailed. That's typically the way it's done in the UK. So you see it's called LIFO, last in, first off. So depending on when they connect, they get their connection agreement stamped and they build say, their wind farm. So the people who built their wind farm in 2005 will be turned off after the people who built their wind farm in 2010. So that's the way things are managed on the distribution network to resolve constraints. There are better ways to do that. If you wanted to minimize curtailment, then potentially you would curtail the person who had the biggest impact, who you were going to get the best, say, bang for your buck at the constraint, or you could also run a financial and economic thing there. So the person who's the cheapest to turn off is going to cause the least financial damage would be the ones who would be turned off. There's a lot of detail to go in there, but essentially that's broadly how it works.
Okay. Yeah, it's good. We will take the 3 hands up in this way. The last part of the question was, is this a contractual agreement? I say yes. I will just help there. This is also in the power purchasing agreement, who pays for what when you supply and when you're not supplied. So there is always cost attributed to that, and it's managed by the power purchasing agreement of each party, each generation company. So I will take the 3 hands up. I will start with Ademola, and then I will take Engineer Shegu, then I will take Victor. So let's go with that. So Engineer Ademola, can you unmute and ask your question, please? Thank you.
Okay, thank you. Thank you, David. I just want to ask quickly, can the looking at the case study in Nigeria, for instance, what is the minimum voltage that you can use for the can you use it at the load side in a situation that you are? I know in UK power is constant. What we do here is that when you install the solar system, you will put your export at 0, so that when you are generating, you don't generate back to the grid. I'm looking at, is it possible to be able to use the DL in a particular zone that has maybe a 1 MVA that is supplying the whole zone, and you now have about 2 or 3, 4 people generating 250 kVA, and so that at that particular area, at any point in time, there will be power, whether it's from the grid or from the other sources. That's my question. Thank you.
Thank you, sir. Engineer Shegu.
So
okay, thank you so much.
Shall I answer that first? Just
Okay, go ahead.
I might forget.
All right.
So what voltage levels? So essentially for the kind of the work we do for the utility companies tends to be at the kind of medium voltage. So from maybe 33 kilovolts, 11 kilovolts. It depends really on the problem that's trying to be solved. So the example you were given there, that is a potential thing that could be done. So that's also almost touching on creating, I guess, a kind of almost virtual microgrid. So using the assets, say maybe, I'm not sure if it was behind a meter, but to kind of use the local assets first to stop import. That sort of thing is possible, yes, on the microgrid project. That is essentially what we were doing to save the townspeople money. And we were using their local assets to try and reduce how much energy they were importing from the wider network.
Okay, good. Engineer Shegu, please, your question quickly.
Yeah, thank you, David. Just two quick questions. The first one is there a minimum capacity that the DER has to have for it to be connected to the grid and manage or control smartly? And the second question is for private installation, for example, solar PV on a roof, which require a G99 application. Are you guys involved in that? Do you also manage such kind of networks to connect to the grid?
Yeah, so first, the first question is not, I guess it doesn't matter too much, but what on the size. So as long as it's controllable, so I guess much of your smaller stuff will probably be behind an inverter. If your inverter is controllable, then well, we can control it, but it depends what you want to do with it. So the answer to your first question is really, it depends on the scenario you want to control. The things that we do, we have not typically, so we don't have any G99 compliant solutions. It's not really the market we're in, but we control the thing that does the G99 compliance, if that makes sense. Yeah.
Okay, thank you.
Thank you.
Victor, please, can you unmute so we take your question?
Okay, thanks so much. Thanks, Dave. Yeah, interesting presentation. Just a couple of questions. Yeah, I'm trying to differentiate the function of the DER against other power management systems that are systems, particularly in terms of managing generators connected to a network. So what you're saying in essence is what makes this matter or more, should I say, desirable is the ability to knock off a generator or a generating capacity of the network, maybe due to overcapacity. If that's the case, I think other power management system does the same work. Sorry if I mean, that's because I work closely to things like that on the offshore side. So I'm trying to understand, in essence, how also the DER can manage fault and reliability in the system. So when you've got a lot of smaller generator connected to the system, and there's an issue with should I say the available power due to fault, maybe that's one of your main generators. How does the system, does it have an outage management system incorporated in it? Does it have asset management system incorporated in it? I just want to see how robust it is, and if it's something that can be deployed outside a regional distribution network.
Okay, thank you very much. This will be our last question. So David, Victor is giving us the last question because of time.
Thank you for that. So I guess I'll try and answer that briefly. So I guess just the first part of your point. So there is nothing unique really about distributed energy resources other than there are lots of them, and traditionally there weren't lots of them. So the special thing is just like having some centralized control over them. I was struggling to hear the second part of your question. Sorry, but I think the crux of what you were trying to say is how can they be managed under different situations. So in our typical deployments where we are just connected DER to the to the distribution network, and we're just managing them against constraints. So we would typically not do any sort of like control for control in, say, contingency scenarios. So that's still up for the network operator to manage. we take account of the contingencies and we maybe change the constraint locations based off the contingencies, but you're not so much using the DER to do anything about the contingencies other than just try to get them to export as much as they want. When you're looking at running a microgrid, yeah, that's when you've got much more control to do cool stuff, do interesting stuff, keep a network live, as opposed to just letting it fail if you lost your main control, your main connection. The final thing I would say is there's quite an interesting innovation project we worked on, we've been working on down in England. It's called Active Response with UK Power Networks, and that is more actively using some innovative DER that were essentially soft back-to-back inverters, and using some more intelligent algorithms to reconfigure the low voltage network in order to reduce constraints before they actually happen. So there are some interesting things you can do. It really depends on what control you have and what you have available to control. I'm not sure if that particularly answers your question, but that's what we've got.
Thank